Now, what we are doing right now with doing Segmentation Framework. So far, we just saw what is old stuff. It's what we know since 15 years now, basically. 10 years. But there are two lines of research that are very active right now in using doing segmentation frameworks, and recently they are start merging. So those are the topics of the few next slides. So one of them is about signatures. What is a signature? Great. A signature is, let's take all hypothetical argumentation frameworks ever. We take a signature of a semantic as the collection of all the possible sets of extension that a doing segmentation framework can have under a semantics. So you have this one. It's telling you eventually what is also the semantics, and it's telling you that those are the extensions for some doing segmentation frameworks. You basically want to have those as the set you want to have out of the computation of the semantics. Right? So you have in your mind what is the meaning of the argument A, the argument D, the argument E, and you want them to be in an extension. Now you can, given this signature, you can compute the set of arguments you are talking to. It's just the union of all those sets. It's pretty easy. So you take all those arguments. And then you can also take this structure called pairs that is defined as, well, two arguments should be in the same of these sets. So A and B are in the same set, A and D in the same set, A and E, B and C, B and E, C and E, and D and E. But for instance, C and D doesn't appear in the pair. In the pairs, sorry. And now you can have some properties about those signatures. You can say that the signature is incomparable if you have that those are maximal. So there is no case that one element of the signature is a subset of another one. Tight, if you have that, if an argument does not occur in some extension, there must be a reason for that. Typically, there is a conflict. This is the idea behind tight. So you actually cannot just put one argument inside one of those extensions. And add closed is basically rewriting the condition for admissibility. And Dune and other people in Vienna proved that a signature is stable if it is incomparable and tight, and for instance preferred if it is not empty, incomparable, and add closed. Which means that if I'm giving you this one, this is a signature. You can compute the pairs in the same exact way we did that before. And you can derive that this signature is incomparable and add closed. And by what we defined before, it means that it is the resulting of a preferred extension. Sorry, preferred semantics. What you can imply from this one? Even if you don't know which one or how many of those are, there is at least one doing segmentation framework for which the preferred extensions are exactly those. Let me repeat. You just have those sets of arguments, but these theorems are telling you that there exists at least one doing segmentation framework that you can create that has those as preferred extensions. And this is an example. You can add other arguments. It's not forbidden. You don't have just to use those arguments. But even in that case, those are exactly the semantics, the extension that you can get out of it. But it's giving you also another powerful tool. I changed the last one from AB in ABD. Now I want to ask you, does exist at least one Dunks argumentation framework that has this as set of preferred extensions? And the answer is no. It's not because you bring inside B and D, and this is making impossible to define it as tight. This is just a glimpse on a new, exciting line of research that is much more big. But this is the basic concept. You have a set of extensions, and you want to define whether something exists, a Dunks argumentation framework exists that can be having those as semantics extensions. They cannot, and other properties out of it. For instance, also, what are the complexity for computing them? Etc. There are plenty of works in this direction. And then there is another direction that is started more or less at the same time, in which I was partially involved, but mainly is Pietro and Massimiliano, clearly. That is about decomposability. I mean, look at this one. Do you really care about this 3-cycle? If you just compute the semantic extension, you don't care, right? It's undecided. It's just dragging you behind. You just want to leave it behind you. So it would not be nice to just remove it and just make it more shorter or simpler. Because you maybe don't care. You just want to summarize that part and say, this is the summary of it, and we do not look at that anymore. And this is basically the idea behind the input-output argumentation framework systems, which is trying to address two questions. One is, given an arbitrary partition of an argumentation framework, can we compute a semantic just as a composition of the different parts? So like here, we just split somewhere this framework, and we just compute one side, another side, and we merge them together. Can we do that? Cannot we do that? And the other one is transparency. Can we just take some part of it, of this framework, and replace it with something simpler, or more complex if you want, in order to have the same result from a semantic point of view for the rest of the framework? And so basically you can have a rather complicated framework like this one, but what you want to have out of it is you just take one of them, maybe want to compute the semantic on one side, and then you might want to just replace everything else with a much simpler argumentation framework. Because maybe you don't care about this part, it's too messy, but if you can just simplify this one, and you really care about this part, you might just want to summarize this part in something much simpler. Which in our case might be equivalent to just say, this has the same effect of the 3-cycle. You just say, this is a self-defeating part, I don't care. I don't care, so I just summarize it. The paper is actually 60 pages long, so it's hard to summarize in few slides, and probably for many of you is not very important, is not probably fitting for your area of research, but I would invite you to read it and cite it. But the key, the takeaway point is we can decompose the computation of some of the semantics. We can for an arbitrary set as well, but not for everything. Like, for instance, not for preferred, not for grounded. And we never talk about semi-stable or ideal, but semi-stable, if you look inside, if you have in mind the complete labeling, the semi-stable is giving you the set of complete labelings that minimize the number of undecided, which means that if the stable extensions exist, then it corresponds to the stable extension. And the ideal is the maximum admissible set that is comprised, included in all the preferred extensions. And as you can see, both of them has very interesting results. Not necessarily positive. And we can also have some transparency results, so that we can basically summarize some part of a framework and substitute it. In general, for preferred, no, but we can add some condition on the structure of the graph. But as we already knew from the SCC recursiveness paper of Pietro and Massimiliano, if you decompose a Dunks argumentation framework on the basis of SCCs, so strongly connected component, then you can have the same result also for preferred. Now, those are two lines of research that looks very different, right? One of them, as Tav was saying, basically you have your wishful thinking there, and the other one is say, well, given a Dunks argumentation framework, you can take out some part, or you can summarize some of them, you can focus on some area, or just merge the computation of extension of two different parts. And this year, well, Massimiliano, Thomas, and Stefan work in the direction of merging those two line of research, sorry. So let's suppose that you just care about some subset of arguments that are called input and output for convention, basically. And you just say, okay, if you have some condition of the input, then you want to have some results on the output. So you just have a table. This is a wishful table. But instead of being for the entire graph, it's just for some subset. Just look at something that you call as input, and just want to see the effect on an output, and this is what you would like to have. And the question is whether you can actually find out a possible transformation, a possible specification that does have at least one Dunks argumentation framework behind. So you just have your wishful thing, but instead of specifying for all the arguments you have in mind, you just specify for a subset that is your input, and you just want to have that the result will affect the output in a specific way. So the theorem is giving you some conditions under which one you can have it, but I just want to give you the idea of how you can identify them. You basically try to find Dunks argumentation framework where you inject one argument of the input at the time, and you want to have the exact result for the output. So let's consider whether this might be a suitable candidate, and let's inject neither A nor B, which is this one, and this is actually telling you, okay, C is then in, and M is out, and that's fine. And then let's inject A. Sorry, the alternative is either C is in and M is in, or D is in and M is in as well, so that's fine. Let's take A as in, which means that your fictitious argument that you use just to inject arguments from the input are attacking B. So you just look at A, and A is giving you that D is in, and M is therefore also in, which is exactly what you would like to have here. Vice versa, M in, C is in, and M is in. And what happens if both of them are in, so your fictitious argument here doesn't have anything, then you can have that F is in, which makes M out, which is exactly your wishful thing.